All right, let's see how we can use this keto-enol tautomerization to do some reactions with it. So in this case, we're going to take a look at alpha halogenation under acidic conditions. And generally, these acidic conditions are actually going to be more useful than the basic conditions for the halogenation, at least. So what we're going to do is take some kind of ketone, add some acidic water, and then add some of our halogen, right? Because we're doing halogenation. And then we're going to add that halogen on that alpha position, where this X can be chlorine, bromine, or iodine. So fluorine's not able to do this, but our other halogens are. In terms of the mechanism, it's not too bad. We have our ketone, we have our acidic conditions. It's just going to go ahead and pick up this H+. After this, we can have this hydrogen be deprotonated by water. And then show our resonance structures to get to our enol form. Note all of these arrows actually should be resonance arrows. All of these reactions are very well reversible. And then what we're going to do is we're going to reform our carbonyl. So we're going to kick this down, and then we're going to have this carbon-carbon pi bond attack our electrophile, which in this case will be our Br2 or our X2. And then it'll kick it off there. Note that when we're drawing these reactions, it's the alpha carbon that's nucleophilic. And then if we think about a product, there's going to be a proton transfer to get rid of the hydrogen on the carbonyl, but we'll end up with alpha halogenation, right? So you can see how we've added it in there. And generally in these acidic conditions, it'll stop with adding just one halogen. So for example, if we had this ketone, if we added some acidic water and some Br2, now we have two alpha carbon positions. And then we can think about which position is more likely to receive that Br. If we think about our intermediate, it's going to be an enol, which includes a carbon-carbon double bond. And remember our rule with alkenes, the more substituted alkene is more stable, right? So this is going to be the preferred enol form. More substituted alkene, it's going to write better. And so when we think about where that bromine is going to end up, it's going to end up on the more substituted position as the major product. Obviously, you are going to get a mixture of everything. And then once we have this alpha halogenation, another thing we can do is we can add a base such as pyridine and some heat. And now we've got a good leaving group. We've got a beta hydrogen to that bromine. And so we can do an E2 elimination to form an alpha beta unsaturated ketone, which we'll see will be useful later on.